Hello, I'll be introducing our work, Dynamic Mesh Recovery from Partial Point Cloud Sequence. This is an overview of our work. Our model takes point cloud sequence as an input and generates recovery mesh sequence. We use parametric models to represent mesh model, SMPL to represent human mesh, and Mano to represent hand mesh. We utilize two-stage network to effectively handle partial sequences, the kinematics learner and the feature follower. The kinematics learner learns the feature encoding of the complete sequence and learns to estimate the parameters for mesh reconstruction. We use transformer-based conditional VAE architecture for post-parameter generation. This is a closer look on post-parameter generation from input point cloud sequence. Our model firstly encodes point clouds using pointnet followed by the transformer encoder. Pointnet features are inserted to separate transformer channels. Temporal index is subject to positional encoding to embed timestamp information to the feature. Features are then used to generate prior distribution. Ground truth post parameters are combined with features to generate posterior distribution. Sampled latent ZT are combined with the feature FT, then inserted to separate transformer channels to generate the post parameter estimates. After training the kinematics learner, we train the feature follower to estimate the parameters on noisy partial sequence. When training the feature follower, we freeze all the layers in the kinematics learner and train the feature follower to successfully recover mesh from the input. We test our model on 3 motion datasets: synthetic human motion, real human motion, and hand motion. For human motion, we first train the kinematics learner with a large-scale dataset of AMAs. Surveyor and Berkeley MHAT are an order of magnitude smaller in size. They are used to train the feature follower and evaluate the performance. This is the result of our model on synthetic point cloud, emulating the measurement from a single depth sensor. Despite the partial observation, our approach can closely follow the motion of the ground truth mesh with the power of the strong latent space. We compare our results against 2 other recent baselines that also estimate the SMPL parameter. Note that the baselines lack temporal continuity and suffer from ambiguities in the noisy input. Here are more results of our model and the baselines on human synthetic motion, which show similar performance achievement. The real data additionally contain wiggling noises and flying pixels. Our method nonetheless recovers plausible mesh sequence, whereas baselines fail to generate realistic motion. Our approach is not limited to humans, but can be applied for any parametric models. We also test the pipeline with hand motion using Hanko and Interhand. Volt HMR-M is our modification of Volt HMR to fit the mono hand model. In the paper, we include quantitative analysis that our method achieves better results. This is the conclusion of our work. We propose a method to fully recover mesh sequence from partial point cloud sequence. Our method outperforms the baselines in both synthetic and real inputs. And finally, our method can be applied to various other parametric models. Thank you.